Okay, so we've been talking about we got into sort of organic chemistry. Organic chemistry is really sort of a transition here for the class in terms of there's really no sort of calculations going on really in these chapters. It's a lot more sort of memorization. We'll talk about some reactions, naming things, drawing things, a little bit more of that type of thing. So we started talking about really organic chemistry, which is really the study of compounds that contain carbon. Carbon really is at the center pretty much of all organic compounds. And really, as we talked about last time, really important to keep in mind, especially in organic chemistry there, carbon pretty much wants to keep those four bonds, make four bonds. Remember, don't have more than four bonds to carbon at any given point in time. But the basic sort of connection for organic compounds are really carbons attached to other carbons. And oftentimes sort of attached to those carbons are hydrogens. And along the way here, we will sort of replace some of these hydrogens with other elements, things like oxygen, nitrogen, and so forth. And it will give us some different types of organic compounds, some different, what are sometimes referred to as functional groups. Functional groups are really the part of the organic compound that sort of makes it part of a certain class. So we started out talking a little bit about carbon-carbon single bonds, which is a class of organic compounds which are known as alkanes. For example, if you had a carbon-carbon double bond, those are a class of compounds which are known as alkenes. You got a carbon-carbon triple bond. Those are guys which are known as alkynes. And for example, if you had an OH group there, that is the functional group for an alcohol. So, switching out some things, having these things sort of present, we'll see later on as well, a carbon oxygen double bond and hydrogen, that's an aldehyde type group. Now, depending on the location or if these guys are present, there obviously are others as well. You'll have these different types of organic compounds. They'll have some different properties based on sort of those functional groups. And they will also have some different names depending on sort of the functional group as well. So understanding the functional group and sort of what class of organic compounds it comes from is really important. Also really important, as we talked about last time, essentially is the first group here, alkanes. Pretty much everybody comes back to really these alkanes, and in terms of naming and so forth, we really just build off of the alkanes order name and change it a little bit along the way. Alkanes, which are all carbon-carbon single bonds, as we talked about last time, have a general formula of CnH2n plus 2. And again, that is basically N is the number of carbons. So again, if we had our one carbon, 2 times 1 is 2 plus 2 is 4. And that gives us really the simplest organic molecule you could have, which is methane. Again, if you had 2 carbons, N would be 2. So 2 times 2 is 4 plus 2 is 6, gives you 6 hydrogens to go with that. And that would be ethane. By the way, that is what I drew up here. These guys end in ANE, and that's because they are alkanes. We also talked about hydrocarbons and the idea of saturation. So a saturated hydrocarbon is something just like this guy here. It basically means we have the maximum number of hydrogens that are there, that could be possibly there. And that's what a saturated hydrocarbon means. Unsaturated, as we will see, means that basically we don't have the maximum number of hydrogens present. So for example, if we laid in there a double bond between the carbons, now, we don't have those extra hydrogens there really because we had to make the bond. And again, this is what we refer to as a unsaturated hydrocarbon. Again, really doesn't have the maximum number of hydrogens present. I think we finished up kind of looking really quick there at sort of a name, one I just randomly, I think, drew. And, you know, when we do go about naming, it is usually follow the IUPAC sort of way of naming. That's the International Union of Pure and Applied Chemistry. They're really the ones that come up with all these rules. Some of which you may think is a little crazy, but we do come up with all these rules and we do want to follow those. So usually when you're naming organic compounds, you want to kind of go through the IUPAC way of naming. Sometimes people even ask you to name it the IUPAC name. And the reason for that is, as we will also see, in organic chemistry, there is a lot of different names sometimes for the same compound. So, you know, you could actually name something the IUPAC way. You could also go by sort of like a common name, which is sometimes used. Sometimes things have a more historical type name that's been used for so long that people still sort of use it and so forth. I might jump the gun a little bit here in terms of naming, but essentially when we do name something, it really does revolve around the first 10 alkanes, as we talked about. And we always want to kind of find the longest continuous carbon chain. So I believe we were kind of looking at this one here at the end. And again, longest continuous carbon chain does not necessarily mean the straightest. Again, here, if we went straight, we would have 1, 2, 3, 4, 5 carbons. But if we went straight and then went up, we ended up with 1, 2, 3, 4, 5, 6 carbons, and 6 carbons would be the longest carbon chain. The importance of that is it will match pretty much one of the first 10 alkane names. And that's, again, sort of your basis of your name. Everything else that's sort of attached to that longest continuous carbon chain are what are referred to as groups. And we'll get into that a little bit more today as well. And groups, as we will talk about, you know, are essentially also based off of the first 10 alkanes, but they are missing sort of a hydrogen, which allows them basically to attach. They have to kind of lose a hydrogen in order for them to attach. Otherwise, again, carbon will end up with too many bonds. As we talked about last time, it's really all about sort of location and name and where everything can be found. So again, if we sort of dissected the name, the base of the name is hexane because of the 6 carbons, which was the longest chain. We had a 1 carbon group that was attached to that chain. And because it's a group, it's not called methane anymore because it's missing a hydrogen. It is known as a methyl group. And we also need to give the location where this group is located. And that is where the sort of 3 is located at. Any questions on the stuff we started talking about last time? Okay, so maybe coming, maybe there it is. So here is a table, I think, from your book. And again, you know, if you want to, excuse me a sec here. There we go. If you want to sort of, you know, do pretty good in terms of organic chemistry, really the faster that you sort of know these first 10 alkanes, both the formula and the names, the much easier it is to actually go about naming everything. So just to review, we have our methane, which is 1 carbon, 4 hydrogens, ethane, propane, which is 3 carbons, butane, which is 4 carbons and 10 hydrogens, pentane, which is basically 5, is 5 carbons, hexane, which is hexa, like 6 carbons, hepta, which is 7, octane, nonane, and decane. We also talked about some different types of formulas. This is the molecular formula, which basically just tells you what's there. We got our condensed structural formula. Condensed formula basically means that we are not drawing out the hydrogens here. So we don't draw out the hydrogens. And that's different than what I drew a second ago, which was this, which is sometimes referred to as the expanded structural formula. which basically means we draw out the hydrogen. So that's another sort of one. And we also have line structure over here. And remember, we talked a little bit about it last time as well. Line structure, basically, that's it. We really don't put anything else on there unless it's a different element. But a reminder that pretty much everywhere where the line stops, where it comes to a point, is a carbon. So there technically would be a carbon here. There technically would be a carbon here, and carbon here. And again, if we sort of were to draw this guy out, we would have a carbon attached to a carbon, attached to a carbon, attached to a carbon. And remember, the importance of carbon needs 4 bonds. And that means if there's no other element involved, all the rest of the bonds to get each carbon to 4 would be hydrogen. So this guy at the end here would have 3 hydrogens. This guy here has 2 lines coming in, which means he gets 2 hydrogens. This guy has 2 lines coming in, which means he gets 2 hydrogens. And this guy at the end would also get 3 hydrogens to give it 4 bonds. So this sort of guy without the little dots on there, this guy is the same as this guy. And that guy is the same as if you wrote CH3, CH2, CH2, CH3. This is the same thing as well. So those are all 3 representations of the same guy that has 4 carbons, which is our good guy right here, butane. And again, this is what is sometimes referred to as line structure. This is obviously our expanded structural formula, and this is our condensed. Any questions on that there? I believe on this table here, the line structures are off. So this actually has 2 carbons, 1 at each end. So that would be actually ethane. So I don't know if it's better in the book or it just happens to be on the slide, but they're kind of off. So obviously the one we just did there is butane, which is right there. So just for reference point, those line structures kind of go one down. There's really no line structure for methane because there's only 1 carbon. So can't really draw a line without 2 points. So you don't really do a line structure for carbon, for methane, because there's only 1. So again, all these just basically 1 down. So definitely want to make sure you got the name, you got the number of carbons. It is definitely key to when we fully get into naming some more stuff here. Condensed formula, as I mentioned before, again, don't draw out the hydrogens. But as we talked about, I think last time as well, it's important. Sometimes people maybe misunderstand this when they look at this sort of condensed formula. Again, remember that all real organic sort of connections is actually the carbon to the carbon, and the hydrogens are attached to the carbon. So sometimes when sometimes when people will sort of do this or try to turn it into the expanded one, obviously there's more carbons like I just drew on the last slide here. It should look like this. Sometimes people, when they would go to maybe turn this into the expanded one, misunderstand the connection that's happening there. And sometimes people will draw it, something like this, where the carbon's attached, they fill to the hydrogens that's attached to then the carbon and then the hydrogens. And this is obviously incorrect for several reasons. It is carbon to carbon, but as even just from our basic Lewis structure conversation and whatever chapter that was in, we know for sure hydrogen should only have 2 electrons, which means it should never be in the middle. So that's never the way the connection should be. Like normal, hydrogen should only have really 1 bond to it. It should always find itself like we see here on the outside. Otherwise, if you put it inside like I did there incorrectly, you will definitely have way too many electrons. Any questions on that there? Okay, so alkanes are written again a couple different ways. Expanded really just means that we're going to be drawing out those hydrogens. Condensed, we're not. Sometimes even with a condensed formula, if you do have like a lot of, so for example, if you had like this deal here, just keep drawing. Just keep drawing. So sometimes you'll even see in a sort of a condensed formula, a even more condensed formula, if you will. If we look at this, we got basically 1, 2, 3, 4, 5, 6, 7, basically CH2 units in a row. So sometimes people will condense it down even more to CH3, CH2, and then put on the bottom, what did I count there? 7, I think, right? 1, 2, 3, 4, 5, 6, 7, 7, and CH3. Again, this 7 just means that we have these 7 units that basically repeat. So if you see a formula like this, it just means whatever in the parentheses basically would repeat however many times there is with that number there. Any questions on that? Obviously, line angle formula. I personally just call it line structure. Some people call it skeletal formulas and stuff like that. But again, we typically see line structure definitely drawn in what is sometimes referred to as this sort of zigzag sort of shape. And the reason for that is, as we also talked about last time, if you look at any of those carbons in an alkane, because they are single bonded, it has 1, 2, 3, 4 electron pairs and 4 bonds, which gives it that tetrahedral geometry of 109.5 degrees. And that's what causes this sort of zigzag shape that we see here. What I drew here, again, everywhere there's a point, everywhere where a line ends is a carbon. So there would be 1 carbon here, 2 carbons there, 3 carbons, 4 carbons, 5 carbons, 6 carbons, and 7 carbons with nothing else written. Again, that is going to be heptane, 7 carbons. And again, what else is really there is our hydrogens. So again, this guy at the end would have our 3 hydrogens, which is normally not drawn in this type of structure, and 2 hydrogens there, obviously 2 hydrogens here, 2 hydrogens here, 2 here, and 2 there, and 3 at the end. You can maybe see that for the most part, 3 at the end, 2 in the middle in alkanes, as long as there's no double bonds or anything like that. Any questions on that? Okay, so we've talked about some of these things. Truthfully, we don't really do too much of ball and stick type of formula, but we do see expanded structure a lot. We do see condensed a lot, and line structure does come around there a lot, and we do use the molecular formula, so not too much ball and stick type model. Now, if we look at something like butane here, we do have this butane right here. And it's important, you know, especially when we talk about, for example, something like isomers or something. It's this idea of, as we'll talk about, isomers are basically the same molecular formula, but a different connectivity. And sometimes people think that they're actually perhaps drawing different structures because they simply, you know, draw it a different way in a sense. So what I mean by that is you may be looking at all these structures here, and it may appear to you that they're all perhaps different things. But in reality, if you follow the really main rule about organic chemistry, which is you always want to find the longest continuous carbon chain. So for example, in our expanded one, it's pretty easy to see. That's 1, 2, 3, 4, which is obviously butane. And obviously here in our condensed, it's 1, 2, 3, 4, which again is butane. Now you may look at the guy below it and go, well, that's definitely something different, but it really is not. If you just go this way, that is 1, 2, and then down, 3 and 4, still butane. So I drew it up and down here. So still 4, 1, 2, 3, 4. This one guy up and the 3 straight across, starting here, 1, 2, 3, 4. Up and down there, 1, 2, 3, 4. Straight all down, 4, and zigzag here, 1, 2, 3, 4. the longest continuous carbon chain in every single one of these, even though they may all look completely different, are all 4 carbons in a row. There's absolutely nothing else attached there, which means every single one of them are butane. There's nothing different there. And again, sometimes people think, well, it looks different, so it must be a different sort of compound. And it's really important, you know, when you, again, get sort of the naming part of it down, that's a very good way to decide, you know, did you actually draw maybe something different, or did you draw something that really is the same? So for example, if we took butane here and we ran only 3 carbons in a row, and we laid up a carbon coming up this way. Now, when we look at this guy here, the longest continuous carbon chain, if we were to count it, is 1, 2, 3 if you went that way. It is 1, 2, and 3 if you went up. There's also obviously 1, 2, 3 if you went the other way, either way. So 3 in this case, no matter which way you go, is actually the longest continuous carbon chain. And 3 carbons is no longer butane, but 3 carbons is actually propane. And now this 4th carbon actually becomes a group that's attached. And this group is, again, as we talked about the other day, based off of 1 carbon, which is methane. And because it's a group, it is what is known as a methyl group. And this would be methyl propane. And it's at carbon number 1, 2, and 3. At carbon number 2, this is 2-methyl propane. The structure that I just drew is not butane. But if we count up everything that's there, it still has 1, 2, 3, 4 carbons. It still has 3, 6, 9, 10 hydrogens. It has the exact same molecular formula as butane, but it has a completely different name, which means that it is a completely different organic compound. And I actually did draw something that is different. And these 2 guys would be what are referred to as isomers. Isomers are things that have basically the same molecular formula, but different connectivity. And this is what I was talking about earlier. This is the way you could really, you know, check yourself to see if you really did draw something different. Are very commonly done. People will kind of do this move, kind of drop it down, or even this move, drop 1 down, drop 1 up, and go, okay, I drew something different. But again, in each of the ones on the bottom, you would come up with the same name of butane. Here, obviously, we got something different. And again, that's basically what an isomer is. Any questions on that there? All right, so let's do that. So let's see here. Given the following expanded structural formula, let's provide the molecular formula, condensed structural formula, and the compound name. So why don't you take a second and go for all those? Why don't you also add the line structure as well? Why not? All right, take a second and come up with all those. All right, let's take a look at this. So the first one's pretty simple. The molecular formula pretty much just count up what we got going on. So we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So molecular formula would be C5. And then we would count up our hydrogen. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that would be 12, and that would be the molecular formula. Off of the 5 carbons, that's really all we need here to know that really this name here is going to be pentane. And if we were to basically draw the condensed formula, we basically would just break this thing into parts based off of the carbons. So to the left here, we have 1 carbon and 3 hydrogens. Next to it, 1 carbon and 2 hydrogens. Next to it, 1 carbon and 2 hydrogens. Next to that one, also 1 carbon and 2 hydrogens. And lastly, at the very end there on the right, 1 carbon and 3 hydrogens together would give us our condensed formula here. And lastly, if we wanted to do the line structure, we basically just zigzag our way until we get 5. So this is 1, 2, 3, 4, and 1 more makes 5 there. Again, a carbon here. You don't have to draw the circles. Carbon there, be 2, 3, 4, and 5. Again, everything else there would obviously be hydrogens. Any questions on any of that stuff, any of those formulas there? Okay, then while we do the condensed structural formula for ethane and heptane, and let's also do, well, we do the line one as well. Why not? All right, take a second and see what you come up with. Take a look. So we'll start with the name. So again, once you got those first 10 down, you will know ethane means 2 carbons. And since it's ANE, you also know that it is a alkane, which has a general formula of CnH2n plus 2, which means then you would know that 2 times 2 is 4 plus 2 is 6 hydrogens. And our condensed formula would look like this. Our line formula would look like that, basically. Again, a carbon at each end. And again, you don't usually put the little circles there. Any question on that particular one there? Same thing rolling this way. Heptane means 7. ANE means alkane. Alkane means this. 7 times 2 is 14 plus 2 is 16 in that case. So the molecular formula here looks something like this. That means we're going to basically, you could do it one of 2 ways. If you're not sure, you could just start with the carbons if you want. Just lay in there. 1, 2, 3, 4, 5, 6, and 1 more makes 7. And again, remember that carbon needs to end up with 4 bonds, which means everything else usually is going to be hydrogens. So if I look at the guy on the left, it has 1 line coming in, which counts as a bond. That means it needs 3 more hydrogens to make 4. The guy next to it has a line coming this way and a line coming that way, which is 2 lines, which means he needs 2 hydrogens. Same with the guy next to him. He also has 2 lines, which means he needs 2 hydrogens to get to 4. Guy next to him, same thing, 2 lines, needs 2 hydrogens to get to 4. Same thing here, 2 hydrogens to get to 4. Same thing here. And the guy at the other end only has 1 line coming in, which means he's short 3. He would need 3 hydrogens there. Question on that there. And our line structure, again, would zigzag our way to 7, which I think I did. 1, 2, 3, 4, 5, 6, and 7. Any questions on that there? All right, so next thing we're going to talk about are cyclic alkanes. Cycloalkanes are basically ring structure type things. So there's a few different types of alkanes. There is what is sometimes referred to as the straight chain, which is kind of like, I'll go this way, is just a straight run of basically carbons and, attached to carbons, nothing else happening. Just straight across, straight chain. There's also what is sometimes referred to as a branch chain. And a branch chain is kind of like what I drew a second ago, something like you know, where you have a main chain and you got, like on a tree, some branches of some stuff coming off of it. Could be as simple as that. Could have multiple, you know, things branched off, you know, along the way here. And again, making, you know, all these different sort of branches, points off of the main sort of line. And then you have a ring type structure, which are cycloalkanes. And they basically are alkanes where you kind of take both ends and kind of put them together. And they have a general formula of CnH2n. And you notice it's missing the +2 part. And that is because in order to put them together, you got to lose a couple of hydrogens. So for example, if we look on the bottom here, looks like they got propane, and we have cyclopropane. Now, basically the difference between the guy on the left and the guy on the right is a closed ring type structure. And that means that these guys basically came together. Now, if I decided just to bond them together like I just drew it, we do end up with a problem because the carbon on the left there and the carbon on the right will end up with 1, 2, 3, 4, 5 bonds because there's 3 hydrogens bonded there, and would be too many. So what ends up happening is we actually will lose 2 hydrogens for every bond that we make. So every kind of bond that we kind of put onto an organic compound, we basically will lose 2 hydrogens. 1 from each carbon is typically the case there. And that is why we don't have the +2 part here. These guys are typically kind of drawn like shapes, if you will. Like cyclopropane pretty much is usually drawn in line form like a triangle. And again, that is 1 carbon, 2 carbons, 3 carbons. But again, each of these only have actually 2 hydrogens at each point. And again, gives us 3 carbons, and 3 times 2 is 6 hydrogens, which is what we see based off of here. We lose 2 hydrogens as we make that extra bond to close it up. So these guys are a lot of your geometrical type shapes. You have your triangle, which is 3 carbons based off of propane. And as you can see, you put cyclo in front of it. So this is cyclopropane. And if you had like the square, if you will, square here has 1, 2, 3, 4 carbons. 4 carbons is based off of butane. It is a ring type structure. This would be known as cyclobutane. Because of it, this cyclobutane has 4 carbons and 8 hydrogens, 2 at each corner here. And that is different than just straight up butane, which is our 4 carbons in a row that I think I drew earlier today. Actually right here, 1, 2, 3, 4 carbons in a row. And we have 8, 9, 10 sort of hydrogens. So again, if you kind of think about it, you know, as like this carbon, for example, and this carbon come together, we do need to sacrifice basically a hydrogen off of each of them to kind of close it up into a ring type structure. Any questions on that? And again, in terms of naming, we simply, if there's nothing else attached, we just simply put cyclo in front of the alkane name. Again, if there's really nothing else sort of attached. Any questions on that there? Here's again a chart of our guys here. We got cyclopropane, which again is our triangle, our square, our 5-member guy here. Again, 1, 2, 3, 4, and 5. 5 based off of pentane. And we put cyclo in front of it as it's a ring structure. This is cyclohexane here. Again, a 6-member ring all the way around there. And again, 6 carbons based off of hexane. And again, we put the cyclo in front of it because of that. Any questions on that one there? All right, so let's take a look here. All right, so give the name for each of these to see what you come up. Okay, so let's take a look. And again, biggest thing, always 100% of the time when you are naming things, longest continuous carbon chain. So that's, always keep that in mind. That is always the deal. That is always what you're looking for. And in this case, pretty straightforward. There's no ups and downs, there's no branches. So just kind of count 1, 2, 3, 4, 5, 6, 7, and 8. 8 carbons is octane, ANE, all single bonded going on through there. Over here, if we go to our ring structure here, we also would count it. So that is 1, 2, 3, 4, 5. 5 is based off of pentane. It is, again, a closed sort of ring structure, which means it then gets the cyclo part in front of it, and that would be cyclopentane. Any questions on any of those two there? All right, so taking a look at this one, we'll do kind of the same deal. We want to, again, longest carbon chain. So first one here, 1, 2, 3, 4 carbons. Again, nothing else attached there. So 4 carbons straight across there is going to be butane. This is a closed sort of ring structure here, which has 1, 2, and 3 carbons. So as we saw a second ago, 3 carbons based off of propane. Closed structure here gets the cyclo part in front of it, and that would be cyclopropane. Counting off our condensed structure here, 1, 2, 3, 4, 5, 6, 7. I got some stuff in the way. 8 going on here. Again, really nothing else attached there, just straight across carbons and hydrogens, and 8 carbons is octane in this particular case. And lastly here, counting this guy off like we just saw there, 1, 2, 3, 4, 5, and 6. Again, 6 carbons based off of hexane. We do have to look at it, and we see it's not a straight chain like above, but it is a closed ring type chain, and that would then get the cyclo as well, and that would be cyclohexane. Again, having the formula of CnH2n in this case, because it's a closed structure, which means we have 6 carbons and 12 hydrogens. And again, if we were to draw sort of the condensed structure for that, it would look something like this. Something like that. So again, 2, 4, 6, 8, 10, 12 hydrogens and 6 carbons. Any questions on any of those there? Okay, so now we got some of the bases here of straightforward sort of naming. Let's again talk about what happens when we start really adding certain things to these chains. They're sometimes referred to as substituents. And basically, substituents are groups that are attached to the main chain. And again, the idea here is the longest continuous carbon chain is really like, like a tree, like the main part of the tree there. Anything else is not part of it, or like branches or groups that are basically attached to it. And that's what we look here. So we did this guy a little bit a second ago. Actually, when we look at this here, that's just 4 carbons straight across, which obviously is our butane. And as we saw last time in this combination here, really 3, and you could get 3 in multiple ways to be your longest continuous carbon chain. Here, 3 is the longest continuous carbon chain, which does give us that base of propane. And now we do have this group here, which again is attached to the main chain, but different than being part of the main chain. And it's actually based off of methane because it has 1 carbon. So because it does have 1 carbon, you know, you could think about methane, which looks like this. And the reason why that group there is really not methane is, as I mentioned before, if I wanted to attach methane to another carbon and just the way it is, and I decide, well, I'm just going to go attach this to another carbon. The problem with that is now the carbon in methane has, again, 1, 2, 3, 4, 5 bonds, which is not helpful. So when these guys kind of become a group, and they're sometimes referred to as an alkyl group, YL, they basically will lose a hydrogen, and by the loss of the hydrogen, or have 1 hydrogen left, it allows it to be able to attach into a carbon and still have the right number of bonds. So if we take that methane, but we basically ditch one of the hydrogens, we end up with a CH3 group, which is what we see here. And right here, that's going to allow it to attach to another carbon. Now, when it attaches to a carbon, the original carbon there and sort of the methyl group has only 4 carbons, or 4 bonds. So it's perfectly good. And again, because this is an alkyl group, we really dropped the last part of the ANE. And this guy is what is known as a methyl group, as we saw earlier. And we would incorporate that into our name here, which would again be methylpropane. And given the location of that group, no matter which way you go, that location there is carbon number 2. So when we do have these groups attached, we do want to basically also refer back to the first 10 alkanes. We want to basically kind of mess with the name a little bit there and, you know, kind of get a group because it has 1 hydrogen less. Any questions on that there? Okay, then let us keep going. So we touched upon this a little second ago, but let's officially sort of talk about isomers. Again, isomers are really organic compounds, or really compounds that do share the exact same molecular formula, which basically means they have exactly the same number of elements in each of them. The difference, though, is the attachment. And as we did earlier, both of these guys, if we were to count up everything, they both, again, have the 4 carbons and the 10 hydrogens. But one is butane, and one, as we just saw, there's 2-methylpropane. They have different names, which means they're actually different organic compounds. And that is 100% of the time a great way to check if you actually did draw an isomer. Because it's very common that somebody, for example, will take this and go, okay, cool, I'm going to draw an isomer now. There it is. You know, and they go, well, again, as we saw in that earlier slide, I drew an isomer. It's different than this. So they are isomers of each other. And again, they really are not. And this is, again, why the longest continuous carbon chain is really important, because as we did earlier on that previous slide, if we count the longest continuous carbon chain, that is 4. And this guy is 4. And again, that means that it's actually the same compound. You just drew it differently. And again, if you go back to that slide, you know, they had one going up, one going down, and so forth, are both going down. And again, even though you sort of drew it differently, and maybe in your mind you did draw something different, the best and very convenient way to make sure that you actually did draw something different and that is an isomer, is to actually name everything that you drew. And if you come up with the same name for two structures you drew, you definitely did not draw an isomer. If you come up with different names, and I guess the key to that is if you name everybody correctly, you know, you did draw some isomers. So that's a very good way to basically check to whether or not you actually got the isomers. So again, isomers, structural isomers have the same molecular form with different arrangement. Also does tend to give them some different sort of properties based on their arrangements. Any questions on that there? All right, so why don't you try one here? We got pentane here. Why don't you draw 3 isomers of pentane? So take a couple minutes here. What you're looking to do is draw 3 different pictures of different compounds that all contain 5 carbons and 12 hydrogens. Again, you can kind of name them and see if you did end up with different things. So take a couple minutes, see what you come up with. Okay, so let's take a look here. So obviously one isomer is pretty simple. All you have to do is go pretty much straight across. So I need 5 carbons. So I could just do 5 carbons here. And again, I'll just do the condensed formula here instead of structure, so I'm not drawing everything out. But we'll do 3 hydrogens there. The guy next to it has 2 lines, needs 2 hydrogens, needs 2 hydrogens, 2 lines, needs 2 hydrogens. Guy at the end there needs 3 hydrogens. So this is straight across. We got bad H there. There we go. Fix that real quick. We got 5 carbons and 12 hydrogens going on there. CH2. All right, so where do you go next? Well, where you could go next is perhaps not 5 carbons in a row, but maybe lay up 4 carbons in a row. So I'm going to put 4 carbons in a row next. But now I have a 5th carbon I got to put somewhere. Where should I put it? Should I put it at the end? Well, I'll do that for a second here, and we'll see why maybe that's not the best decision. So let's just say I decide to throw it at the end here. Put in my hydrogens, right? All right, we'll leave that one up there for now. Let's then put the 5th carbon second in from the end. So now we'll put in our hydrogens. This guy only needs 1 as it has 3 lines. This guy needs 2, and this guy needs 3. Maybe the next thing I want to do is just go maybe 3 carbons in a row. Now I need to put my other 2 carbons somewhere. Maybe I decide to put them both on the center guy. So if I do this, I end up with H3 here, H3 here, no H in the center because he has 4 lines, H3 there, and H3 there. All right, so we got at least 4 up here. So let's see, did we actually draw 4 isomers or not? So this is where we would want to perhaps go through and name to make sure we end up with different names. All right, longest continuous carbon chain here is 1, 2, 3, 4, 5. Nothing else there attached. So that is our good friend pentane in terms of the name. Now remember, I was a little hesitant on this one. So let's take a look at this one. Again, we want to start with the longest continuous carbon chain. So that is 1, 2, 3, 4, and then I could go up to continue, which is also 5, and nothing else would be attached. This guy, again, even though he looks different, is pentane. These are the exact same thing. That means that this guy is not an isomer. And again, by naming it, we could realize that hopefully by just putting it at the end, all we did is kind of put it up or put it down. Any questions on that there? Let's take a look at the second guy we did there below. Longest continuous carbon chain is 1, 2, 3, 4. Also 1, 2, 3, and 4 if you went up. So you could have went this way, 1, 2, 3, and 4. But if you do have sort of a choice there and 4, you got like a straight one, that might be a good one to do. So 4 carbons in a row is not pentane, it is butane. That then means that we do have this 1 carbon containing group hanging out here. That is, again, based off of methane, which is a methyl group. And that would be methyl butane. And lastly, we want to number, and I think we touched upon it last time, but we do want to number the main chain. And you could do it left to right, which means this would be 1, 2, 3, and 4. Could also go right to left, which means that this would be 1, 2, 3, 4. You always want to choose whichever way in this case gives the group the smaller number. And in this case, it is the red way, gives the group at carbon number 2. So this would be 2-methyl butane. Again, we put a dash between a number and a letter. We put a comma between 2 numbers. So in this case, 2-methyl butane. Different name, that would be an isomer. So these 2 are isomers. Any questions on that so far? Rolling through on our next one, we want to look for our longest continuous carbon chain. So in this case, many different ways you could get there, but it is 3. You could go that way, you could go this way and up is 3, you could go this way and down is 3. You could actually go straight down from the middle, also 3. But no matter which way you go there, 3 looks like a winner. 3 carbons in the longest carbon chain gives us the base of the name as propane. In this case, we actually have a methyl group attached there and a methyl group attached there. So we actually have 2 methyl groups. And whenever we have 2 of the same group or more, we do use prefixes. They don't have to be on the same carbon, but within the compound, if we have 2 or more of the same group, this would then become dimethyl, because there's 2 methyl groups within the compound. And we do need to give the numbering of where we can find those. And in this particular case, no matter which way you go, this is carbon 1, carbon 2, carbon 3, or if you started right to left, carbon 1, carbon 2, carbon 3, both of these methyl groups are on carbon number 2, which means we would add 2, 2, number, dash, number, letter, dimethyl propane, which is obviously a different name than what we got going on above, which means that would be 1, 2, 3 isomers. Any questions on that? Now, if you felt like, hey, I want to draw another isomer, you do again need to be careful. If you did this and you went with your 4 in a row and decided, hey, I'll just draw the 5th carbon this way. And again, you may look at this and rightfully so look at it and go, looks different than all the other ones that I drew. But again, this is where the naming part of it's really important, because if you went to name this guy, you would then have 4 carbons in a row, which is butane. You would have a methyl group, and that methyl group would be on, if you numbered right to left or left to right here. Oops, get a pen on that. There we go. This would be carbon 1, 2, 3, 4, or if you went the other way, 1, 2, 3, 4. Going this way gives you the smaller number and gives you 2. So again, although this guy on the right looks different, It is actually the same compound that we drew right here second. Any questions on that? And again, that would make this not another isomer. So there is something to be said about taking the moment or second or two there just to quickly run through the names of what you draw. And again, if you A, name them correctly, and B, end up with different names, you probably most likely drew isomers. Again, if you end up with the same name, which obviously could happen, I did it twice here very easily, then you know you didn't draw isomers. Any questions on isomers there? All right, so back to sort of substituents and how we sort of name some of these guys. As I mentioned a second ago, really, you know, a lot of carbon-based substituents, which are, again, these groups that are attached, they are referred to as alkyl groups. And that really is how we go about naming them. So you could take any of those really first 10 alkanes. And, you know, for example, if you had a propane, that would be CH3, CH2, CH3. And you took off a hydrogen, CH3, CH2, CH2. That would allow it to attach here to a carbon. And this part of it here would be known as a propyl, YL, just like YL here, group. Just like our methyl group is based off of methane. If we had a 2-carbon group attached, it would be an ethyl group, and so forth. We also sometimes very commonly see the halogens, which again is group 7 on the periodic table. And that is our fluorine, chlorine, bromine, iodide. And they get kind of like the O ending. So fluorine becomes fluoryl group, chlorine becomes a chloral group, bromine becomes a bromol group, iodo is a iodine group that is attached. So we basically name these groups just like that. And again, our alkyl groups really based off of our first 10 alkanes. Here's a table of some groups, and there are some special sort of groups, names that are commonly seen. Again, these are all alkyl groups. This is our methyl group. Again, one hydrogen less. One hydrogen less. That's our propyl group, one hydrogen left. That's our butyl group. But there are a couple that are slightly different sort of groups, and they have some slightly different names. This is one that we come across a lot. This is what is known as the isopropyl group. It has this arrangement, CH3, CH, CH3. It has a special name, which is isopropyl, and it is seen a lot. This is isobutyl, also has a very similar sort of thing. It has that CH3, CH, CH3, and one more carbon attached there gives us our isobutyl group. And this is because of where the attachment basically occurs. When we look at carbons, we can actually classify carbons as either being primary, and that has like a 1 and a little circle type thing. We could classify carbons as being secondary, which means it has like a 2 and a little knot type symbol. And we could have a tertiary carbon, which would have a 3 prime. So what is the difference between them? Well, pretty much this is the way you can determine is it primary, secondary, or tertiary. So let's say, for example, we had this sort of arrangement here. All right. And let's say we wanted to classify this carbon right here in the box. A couple different ways you could do it, but probably the easiest way to do it is to look at the carbon you are interested in classifying, and all you simply has to do is decide how many carbon atoms there are directly attached to it. In this case, there is exactly 1 carbon atom attached to the carbon we're interested in. 1 is primary carbon. So that guy in the box would be considered a primary carbon. If we had this sort of arrangement, and again, if we're looking at our guy in our box, if we look at the carbon that's in the box and we simply count how many carbons are directly attached to it, that is one carbon, that is two carbons. That is what we refer to as a secondary carbon. And lastly, if we had maybe an arrangement, we'll go here maybe. Do it right here. Something like this. Where do we draw it? There you go. And again, if we were looking at the carbon in the box and we want to see how many carbon atoms are directly attached to it, that's one, that is two, that is three, and that is a tertiary carbon. So you could classify carbons as primary, secondary, or tertiary. And this is really what sort of gives rise to some of these different groups that we see. So for example, if we look at propane, which is what propyl is based off of, and isopropyl is based off of, if we just draw propane with all its hydrogens, looks like this. This guy here is propane. And if we were to classify each of these carbons, actually, why don't you do it? Take a second. Classify each of those carbons as primary, secondary, or tertiary, and see what you come up with. Okay, so let's take a look, and to help you maybe see it a little bit better, we're going to draw the expanded structural formula for propane. So if we drew out all of our hydrogens here, maybe look something like this. Okay, so let's start with the carbon right here on the left. Again, we are looking at how many carbons are directly attached to it, and that would be just one right there. That is a primary carbon. If we look at the carbon in the center, our carbon in the center there is attached to one carbon and two carbons, which means this guy is a secondary carbon. And if we look at our last guy here, I'll just put a circle around him. That guy is directly attached to only one carbon in the middle, which would mean that this is a primary carbon. Any questions on that classifications? So remember that when we turn something like propane here into a group that's attached, we pretty much has to get rid of one of the hydrogens. So if we get rid of any of the hydrogens on the left-hand side or the right-hand side, so any of these hydrogens, they're all what are referred to as being equivalent to each other. The attachment point would end up being at the end, which is what we see here. And that's why this is what is referred to as a propyl group. Sometimes people refer to as an N-propyl group, like a normal propyl, regular run-of-the-mill propyl group. But we can also find attachment here with this propane by taking out one of the hydrogens in the center instead. So if we took out one of these hydrogens, which are both equivalent from our secondary carbon, the attachment point now moves to over there, and then attaches at that secondary carbon, which gives us a different group. And this is sort of a historical name, which is known as isopropyl, and sometimes used to be called secpropyl because it's a secondary carbon where it came from. But isopropyl is a very historical name that is used a lot. So the attachment of where these guys come from gives us different groups as well. We see the same thing with our butane here. Attaching at the end here to our primary carbon gives us like a normal butane. But if we attach it to the attachment point ends up being over here, actually that's isopropyl as well because it has it. But you know, if we attach at a different carbon, you might end up with sort of a tertiary, a tert butyl, which is this guy here. Actually, there's a third one that sometimes comes across here. Let's do that, this. So if we actually attach here at this carbon in 1, 2, 3, 4 butane, that is a tertiary carbon, and this is what is sometimes referred to as a T-butyl group. T meaning tertiary carbon is where the attachment comes from. So again, just simply the different spots where you attach can give you some different group names. For us, pretty much isopropyl, maybe isobutyl there are probably two groups that, you know, are kind of the only strange ones that we'll come across. But there are obviously some different ones along the way. Any questions on that there? Okay, so let's take a look here. So why don't you give this a go? We want to name this guy. So the goal here is to find the longest continuous chain. You want to find what groups are attached. You want to put those groups in alphabetical order, and you want to number the chain, giving the groups the smallest set of numbers. So why don't you try that and see what you come up with. Again, I'll kind of write those steps for you. We're going to go longest carbon chain, find our groups, number our chain, the smallest number to the groups, and put it all together in alphabetical order. So take a moment or two, see what you come up with, and then we'll kind of do it here together. All right, so let's follow our rules here. Everything always starts with our longest continuous carbon chain. So put a little highlight on that. So it looks like it is 1, 2, 3, 4, 5. Other option, we go left, 1, 2, 3, and then go down, but that's only 4. Other option, we go right and go left, 1, 2, 3, and then go down. That's only 4. So it looks like straight across here is our longest continuous carbon chain, and that again is 5. So when you find that longest continuous carbon chain, again, that's going to become the base of your name, which is pentane. Now what you want to do is really find out what is attached to that longest continuous carbon chain. And that is basically everything other than hydrogen would be considered groups that are attached. So in this case, we do see a chlorine attached there, and we do see a 1 carbon group here. The 1 carbon group, again, is an alkyl group. It is based off of methane, but because it's a group, we drop the ANE and put YL, and it becomes a methyl group. As we just saw a second ago, chlorine becomes a chloral group. So now we got our groups here. The last thing that we really want to do is give the location of where all these guys are. So we really have 2 ways that we could go. We can number left to right. So if we number left to right here, this would be carbon 1, this would be carbon 2, this would be carbon 3, carbon 4, and carbon 5. And going in this direction, we would have a chlorine at carbon 2 and a methyl at carbon 3. Now, if we numbered the opposite way, which is our other option here, going with this guy being carbon 1, this guy being carbon 2, carbon 3, carbon 4, and carbon 5, kind of the purple way, if you will, we will end up with a methyl group at carbon number 3, and we would end up with a chloral group at carbon number 4. First off, any questions on those two options there? When we number, the deal is always smallest number wins, and it is as simple as 2 is smaller than 3, which means we would not want to number this way, and we actually would want to number this thing going in the red, the blue direction, actually, it looks like in this case. So we'll get rid of the other way of numbering here. So this would be the proper way of numbering. And since we lock ourselves into that, that means that this guy is going to be a 2-chloral, again, a dash between a number and a letter. This guy would be a 3-methyl, again, a dash between a number and a letter. Any questions on that there? All that's left at this point is to put everything together alphabetical, regardless of number. So C would come before M, also regardless of prefix, if there happens to be a prefix. And putting that together would get us 2-chloral, 3-methyl, and pentane. Again, dash between number, letter, dash between letter and number, dash between number and letter there. And that would be it. Any questions on that name there? And those really are sort of the steps that you definitely want to follow when you go about naming these guys. Let's talk a little bit here about cycloalkanes that also can have substituents on it. If you just simply have one group attached, so for example here, longest carbon chain would be the entire ring here. Whoops, the entire ring. And that is a 6-member ring that is in a ring structure. So 6 is hexane. In a ring structure, it gets the cyclohexane. And because there's only one group attached, this group is a 2-carbon group. 2 carbons is based off of ethane, and it becomes the ethyl group. We would put that in front, and this would be ethyl cyclohexane. Now, you may be asking, does it need a number, like 1? And the answer is no, because it is the only group attached to this ring, which means it's implied that wherever that group is attached is carbon number 1. So because there's only one group attached, you do not need to give numbers. Again, it's assumed wherever that's attached would be carbon number 1. Any questions on that there? Now, what happens if you did have multiple groups attached to something, like this? So let's just say we had, our good friend here, cyclopropane, and we'll put like a methyl group there, and we'll do like a chloral group there. All right, in this case, we would still kind of do the same thing. Obviously, the longest continuous carbon chain is our cycloalkane here. So that would be our base of our name, which is propane. In a ring structure becomes cyclopropane. We now have our methyl group here, and we have our chloral group. So if we numbered, starting with the methyl group, this would be carbon 1, this would be carbon 2. If we started numbering from the chlorine group, this would be carbon 1, and this would be carbon 2. Now, in this case, it's kind of a tie in the sense of we get 1 and 2, 1 and 2. So what's most important here is alphabetical, which means that M should come after C. And because C alphabetically should come first, we actually would want to give it the smaller number and number in this direction. And this would be something like 1 chloral. I'll try to squeeze it in. methyl cyclopropane. So you do need to give the numbers, and again, you want to give maybe the priority to the one that should come alphabetically first, the smaller number there. Question on that there. Okay, I guess we will lay it up there for today.